Today, we're going to be looking at under what conditions can you swap limits and expectations. In other words, if we have a set of random variables, x of t, which is converging to x with probability 1 as t goes to infinity, is it true that the limit as t goes to infinity of the expected value of xt equals the expected value of the limit as t goes to infinity of xt, which is just the expected value of x? So what we're going to do is we're going to give two big theorems that give us conditions under which we can bring this limit into and out of the expectation. So let's get started. First, it's important to note that limits are easier to work with in the extended reals. The extended reals are the regular real numbers plus negative infinity and infinity. So for example, the limit as t goes to 0 of 1 over t, we're going to call that infinity. And the limit as t goes to infinity of 1 over t is going to be 0. The limit as t goes to infinity of negative t, well, that's the limit that we're going to call negative infinity. So by adding these extended reals, we make it easier to write limit statements. Now, of course, all of these have formal definitions that hopefully you've seen before. I'm not going to go over those formal definitions today. Now, suppose we have a sequence of random variables. So x1, x2, x3, and so on. So each one of those is a random variable. They might be independent, they might not, they might come from the same distribution, they might not. We say that this sequence is identically distributed if, for all I not equal to j, x of I has the same distribution as x of j. So if all the variables in that sequence have the same distribution, we call the sequence identically distributed. Now we call the sequence independent if, for all n, and for all measurable sets a1 up through an, if I look at the probability that the first variable falls in a1 and the second variable falls in a2, and so on up to the probability that x sub n falls in a sub n, then the probability that all of those events happen simultaneously is equal to the product of the probabilities. So this is equal to the probability that x1 is in a1 times the probability that x2 is in a2, all the way up to the probability that xn is in a sub n. So it has to hold. We say that the elements of the sequence are independent of each other if for any finite n, the first n elements of the sequence are independent random variable. Now, if we have both properties, if we have a sequence that is both independent and identically distributed, then we call it IID. The I stands for independent, identically, and then the D stands for distributed. Some people like to put some people like to put periods after the I, after each I and the D. That's kind of redundant, and we don't do it for PDS typically or CDS, so it seems silly to do it for IID. Now for most IID sequences, the limit as t goes to infinity of x of t does not exist. Okay, so why is that? Well, let's suppose that we're dealing with a set of variables x of I, which are IID Bernoulli with parameter p. So each one of those x of i's is either 0 or 1, and it's 1 with probability p. Well, if we start drawing from that sequence, we may get zeros and ones and zeros and ones and so on. But no matter how far out in the sequence we go, with probability 1, there'll always be another 1 farther out. And with probability 1, there'll always be another 0 farther out. So because it never quits jumping back and forth between 0 and 1, we don't have a limit. With probability 1, the limit does not exist. And that's true for most IID sequences. So the sequences of random variables that have limits are typically either not independent or not identically distributed. Here's an example of a sequence which is both not independent and not identically distributed. Say that I take a single draw that's uniform over the interval 0, 1. And x of 1 is just u. X of 2 is u over 2. X of 3 is u over 3, and so on. Now I'm using the same u to define all of the x values. So this is definitely not an independent random variable. If I know the value of one xi, I can actually figure out all the values of all the other xi's. And it's not identically distributed. x1 is uniform from 0 to 1. x2 is uniform from 0 to 1/2. x3 is uniform from 0 to 1/3, and so on. So it's neither independent nor identically distributed. But notice that the limit as t goes to infinity of x of t is the limit as t goes to infinity of u divided by t, which is just 0. And so this is a random variable that converges to 0 with probability 1. Probability that x of t converges to 0 equals 1 as t goes to infinity. Well, what about expectation? Can we bring the expectation inside? Well, let's look. The expected value of x of t is the expected value of u over t. Remember, you can bring constants in and out of expectations. So that's just 1 over t times the expected value of u. U is a uniform 0, 1 random variable, so it has expected value 1/2. So the expected value of x of t is 1/2 times 1 over t. So the limit as t goes to infinity of the expected value of xt is the limit as t goes to infinity of 1/2 times 1 over t, and that limit is just 0. So the limit of the expected value of the x of t's is 0. Well, the expected value of the limit as t goes to infinity of x of t, we just said the x of t's are going to 0 with probability 1, and so the expected value of the limit is also 0. So this is an example where it's okay to bring the limit in and out of the expectation. Is it always possible to take the limit in and out of the expectation? Well, I wouldn't be asking that question if it was always true, would I? So let's take an example of a random variable sequence where you cannot bring the limit in and out of the expectation. So let's look at, once again, I'm going to let a u be uniform from 0 to 1, but I'm going to define x of t a little different. X of t is going to be t times the indicator that u is less than 1 over t. Remember, the indicator function returns a 1 if this is true, and a 0 if it is false. So let's look at an example. Suppose that I roll the dice, and u happens to be 0.3218, and it just keeps going on like that forever. Well, x sub 1 equals 1 times the indicator that u is less than 1. This number is less than 1, so this indicator is 1, so this value is 1. X sub 2 is 2 times the indicator that u is larger than 1/2. Again, this value of u is less than 1/2, so this indicator is 1. 1 times 2 is 2. Now let's look at x3. x3 is 3 times the indicator u is less than 1/3. Well, 1/3 is 0.33333, etc. We're getting close here, but still u is less than 1/3. So this indicator is 1, so 3 times 1 is 3. Well, what about x4? x4 is 1 times the indicator u is less than 1/4. 1/4 is 0.25. So this number is not less than 0.25. That makes this indicator 0. 4 times 0 is 0. And with this example, what's going to happen is all the x's beyond x4 are also going to be 0. Let's just do one more step to see. X sub 5 is 5 times the indicator u is less than 1/5. Well, 1/5 is even smaller than 1/4. So if u is bigger than 1/4, it's certainly bigger than 1/5. So it's 0. And it's zeros all the way down. If I look at the xi sequence, it goes 1, 2, 3, then 0, 0, 0, 0. Okay. Hopefully it's not too hard to see that these x of t's are always going to be 0 eventually. It's just that when they get to 0, it depends on how small u is. So for example, if u is 0.6, then the sequence is 1 and immediately goes to 0. If u is 0.098, then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but it's smaller than 111. And so it goes to 0 at 11 and onward. So just like this example over here, the probability that the limit as t approaches infinity of x of t equals 0 is 1. So as t goes to infinity, these x of t values are converging to 0 with probability 1. What about their expected value? Well, something interesting happens with the expected value. What's the expected value of x of t? This is the expected value of t times the indicator that u is less than 1 over t. Well, the t is a constant, so we can just come out. And I'm left with the expected value of an indicator. And remember, the expected value of an indicator is just the probability that the statement inside the indicator happens. So this is equal to t times the probability that u is less than 1 over t. Well, uniforms have this great property that the probability that a uniform from 0 to 1 is less than some number between 0 and 1 is just that number. If I draw a uniform from 0 to 1 and ask what's the probability that it's less than 0.3, well, I have 0.3 chance of it falling in this region and 0.7 chance of it falling in that So this probability is just 1 over t. And so the expected value of x of t is 1. No matter how large or small t is, the expected value of the x of t in this case is 1. Well, what does that make the limit as t approaches infinity of the expected value of xt? Well, the point is, the expected value of xt doesn't depend on t. Not one bit. It's always equal to 1. On the other hand, the random variable is converging to 0. So the expected value of the limit as t goes to infinity of x of t is just the expected value of 0, which is 0. In this case, you cannot bring limits in and out of the expected value. It just doesn't work. So what's going on here? What makes this situation worse than this situation? And I claim that there are two things that are going on here that make this type of random variable worse than this type of random variable. And if either one of those conditions doesn't happen, then we can bring the limit in and out of the expectation. So let's look at what those two things are. So the first thing that's happening here, that isn't happening here, is that the random variables t times the expected, t times the indicator that u is less than 1 over t, that's a random variable which is getting bigger and bigger as t grows. So suppose that x of t is less than or equal to some random variable y for all t. Now, in the example on this board that I just erased, each of the x of t's were less than or equal to u. Example, for all t, u divided by t is less than or equal to u. But in this case, when the x of t's were t times indicator u less than 1 over t, well, those just could keep getting bigger and bigger. It's possible that x of a million is a million, x of a billion is a billion, and so on. They just keep growing without limit. So our first theorem says that if our sequence is bounded above, and the common term that we use for this is we say that the x of t are dominated by y. If the x of t's are dominated by y, then you can bring the limits in and out of the expectation as long as y has a finite expectation. So that theorem is called the dominated convergence theorem. It's also sometimes called the Lebesgue dominated convergence theorem. So our first theorem of the day says, well, first I'll write down what it's called. Lebesgue. It's really difficult to spell because of G going on there. Dominated convergence theorem. I first learned it as just the dominated convergence theorem, so I'll just abbreviate it the DCT for dominated convergence theorem. And what it says is, suppose we have a sequence of random variables that converges to x with probability 1. And if we look at the absolute value of those random variables, each of those random variables in absolute value is dominated by y. Then, if y has finite expectation, y, because it's greater than or equal to the absolute value of something, we know it has to be a non-negative random variable, then you can bring limits in and out of expectations. So the limit as t goes to infinity of the expected value of xt equals the expected value of the limit as t goes to infinity of xt. So that's very nice. That gives a sufficient but not necessary condition for bringing limits into and out of expectations. So what else was going on with this sequence? Well, one thing to notice about this sequence is that the numbers kept getting bigger and bigger and bigger until they didn't, until they dropped down to 0. Well, that turns out to be a problem. It turns out that if the random variables are always getting bigger and bigger and bigger, or getting smaller and smaller and smaller, they will converge. So as long as the sequence of random variables is monotonic with probability 1, you can swap the limits and the expectations. So this result, this second theorem, is called the monotonic convergence theorem, or the monotone convergence theorem. So our next theorem is the monotone convergence theorem, or MCT. And it says that suppose that we have some set of random variables which are increasing with probability 1. Now, I started off by saying that these random variables are at least 0. It didn't really matter that I put a 0 there, as long as they're bigger than, say, -1,000,000. This monotone convergence theorem is still going to work. But it helps in writing it down to just fix a point, so I fixed it to 0. Now, one of the things that you'll learn if you take analysis is that if I have a sequence of real numbers that is increasing, that is monotonic, it has to converge either to a real number or to our extended real, infinity. But it converges to something. Then limit as t goes to infinity of x of t exists, although it might be infinity. And you can swap the limit and the expectation. So the limit as t goes to infinity of the expected value equals the expected value of the limit as t goes to infinity of the x of t. So this is a fact from real analysis that if you have a sequence of increasing random numbers, increasing real numbers, they have to converge either to a limit or to infinity. And this is the generalization to random variables. If we have this sequence of increasing numbers, then we can bring this limit inside this expectation. Now, I'm not going to prove these theorems. The proof is doable within what we've seen in the class, but I just don't have time to do it in this video. So I'm not going to prove these theorems, but I am going to give you a couple examples of where they apply. So the dominated convergence theorem, we've already seen one example. If x of t is u over t, where u is uniform 0, 1, then we know that the x of t are bounded above absolute value of x of t is less than or equal to u, and the expected value of u, which is 1/2, is certainly finite. So the conditions of the dominated convergence theorem apply. Oh, and we also know that limit as t goes to infinity of x of t equals 0 with probability 1. Therefore, we know that the conditions of the dominated convergence theorem apply, and we can say that the limit as t goes to infinity of the expected value of x of t equals the expected value of the limit as t goes to infinity of x of t equals 0. So that was a nice example. That was our first example. Don't really, well, yeah, let's do another example up here. Suppose that U is uniform once again. And W sub t was 1 minus U over t. Well, in that case, we know that the W sub t's are just bounded above by 1. In this case, W sub t is less than or equal to 1. And again, the limit as t goes to infinity of the W sub t's equals 1 with probability 1. Therefore, we know that that limit exists. So the dominating convergence theorem applies, and we know that the limit as t goes to infinity of the expected value of the WT's equals the expected value of the limit as t goes to infinity of the WT's, which is just the expected value of 1, so 1. And we don't have to worry about proving it individually. So those are some examples of the dominating convergence theorem. Now let's look at some examples of the MCT, the monotone convergence theorem. One place where the MCT is used often is where we're dealing with the sum of random variables. So let's say that x1, x2, x3, etc. are all non-negative with probability 1. Now what I'm going to do is I'm going to form the partial sum random variables. I'm going to let S of n be the sum of the first n random variables. Well, what do we know about these S of n? Well, S of 1 is certainly bigger than 0. But S of 1 is x of 1. S of 2 is x of 1 plus x of 2. So I took S of 1 and added x of 2 to it. So S of 2 is certainly greater than or equal to S of 1 because I added something non-negative to my S of 1 random variable. So S of 2 is even bigger than S of 1. Similarly, S of 3 is S of 2 plus x3. So that's even bigger than S of 2, and so on. And so what that tells us is by the MCT, by the monotone convergence theorem, the limit as n goes to infinity of the expected value of the S of n equals the expected value of the limit as n goes to infinity of the S of n. Now, why is that important? Well, the expected value of the S of n is, the S of n is just a finite sum of random variables. So the expected value of S of n is just the expected value of x1 plus the expected value of x2 all the way up to the expected value of xn. So when I'm talking about the limit of the, as n goes to infinity of the expected value of the xn, what I'm really talking about, limit as n goes to infinity of the expected value of the Sn. I'm really talking about the limit as n goes to infinity of the sum as I goes from 1 to n of the expected value of the x of I, or as it's more commonly written, the sum as I goes from 1 to infinity of the expected value of the xi. And similarly, what we have here, the limit as n goes to infinity of the S of n, that is equal to the expected value of the sum as I goes from 1 to infinity of the x of I. So what this is saying is that if you're dealing with non-negative random variables, then you can bring a summation symbol as I goes from 1 to infinity inside the expected value, and you can bring summation symbols inside the expected value out. And that is going to turn out to be a very useful fact that we'll be using a lot throughout the course in stochastic processes. Thanks for watching.